You need to be patient. Okay.
I'll make this open problem announcement once again in the afternoon, I think, because there aren't many people.
Maybe it's like also like just in the afternoon. Yeah, I think it's fine.
Out of these people, I think if you will want to, but
Yeah, that sounds great.
Yeah. No, you can do it twice. Yes. Sounds good.
Okay, good morning, everyone. Thanks for coming for the first talk. So there's like one announcement for Friday. We changed the schedule slightly. So because of one talk cancellation, now we are going to have 2 open problem sessions and 1 group discussion. People also wanted to have a slightly more interactive section. So if you want to have like an open problem talk, it could be a 10-minute whiteboard talk or like a few slides, then let me know. And today I'm gonna come to some of you individually and try to maybe convince some of you to give a talk, because I think you might have some problems. But yeah, that's it. So we'll have like our first speaker now. So Sebastian. Sebastian is a professor at CISPA Helmholtz Institute for Information Security in Saarbrücken. Before this, Sebastian was a TPFL. I think I've known Sebastian for many, many years now and have been fortunate to work on many things together with him. And Sebastian's going to tell us about exploring similarity assumptions in federated learning algorithms.
Okay. Strange. Okay. Can you hear me? Oh, good. Okay. So we have a early morning talk. I think it's good. So if you have any question, ask me. I'm very happy to answer. And we don't have to go through everything in the talk. No, I think it's more meant give a bit of summary. Many people in this room have even worked on these topics, so you know you're expert. I put some of your papers at the bottom as a citation. I might have forgotten some. Please tell me afterwards. Okay, I will go very quickly here. So introduction, we have seen this many times this week. What are we interested in? We look at federated learning. And in my talk, I will take a bit of perspective from optimization side. So how could we model this problem, this federated learning problem in optimization? Well, we could say we want to minimize an objective function, f of x. X denotes the parameters that is given to us in some distributed form. So we can only access these components fi, and we think of these components being stored on different devices. And contacting this device, asking for information, causes some cost. So I will typically not talk too much about stochastic problems in this talk, just for simplicity. We could, of course, think of all these functions on these clients. They are given just in stochastic form, or the clients have some data. They can sample from their data, or they generate new data to give us information. So there are different ways how to model this federated learning problem. One could also say, oh, actually in practice, the number of clients is really huge. We should not think of n as like a very small parameter, but maybe we just take an expectation over the universe of all clients. But this is a very extreme setting, so I will always keep an n for number of clients. Okay, let's dig right into it. Now, why is this problem complicated? Well, it's not really complicated if you, I don't know, ignore everything from practice. No, you just look at it from optimization view. Well, we know we have algorithms to solve this problem. For instance, we can do something like mini-batch SGD or mini-batch gradient descent. We just ask every device, please send me an estimation of the gradient of your loss function, and then we average these gradients on a single server. And this will be an unbiased estimate of the full gradient, and there is absolutely no problem to prove convergence of these methods. Okay, I will simplify many methods in these boxes, just like give a bit of update equation to keep things simple. When we talk about algorithms, maybe we should always specify what is the output of the method. And often it's like the average of all the iterates, which is maybe not what you do in practice. So I will typically not go into details what exactly is the output. Okay, but just to scare you, what is the typical type of theorem we prove? We need some assumptions. For instance, the function is smooth, which means the gradient cannot change too quickly when the parameters change. And we will denote this by a parameter L. So this L, please try to remember L. We assume convexity. And very often when we look at stochastic problems, we make some assumption on the stochastic noise. And for mini-batch SGD, we can prove a result of this form. So there's one term depending only on the stochastic noise. Stochastic noise gets reduced by number of devices. And there is an epsilon square parameter that somehow measures the accuracy, how accurately we want to solve the problem. And this first term, this is, has also been mentioned this week already. This is what we call linear speedup. By just averaging the noise over many devices, we get a speedup a factor of n. There is a second term, which we call like optimization term. This is purely depends on all these problem parameters that we have defined, L over epsilon times the square of the initial distance to the solution. So this is very standard result in optimization. And basically it tells us also there is no benefit of parallelizing this problem. We cannot, there is no parameter n in the second term. So if it's a very complicated optimization problem, under these assumptions, we cannot solve it faster than L over epsilon, number of iterations. Yeah, so when we think of a linear speedup, we are probably in a regime where the stochastic term dominates, and then we can see adding more devices really helps us to reduce the number of steps we have to do. Okay, what is the focus in, what is wrong with this mini-batch algorithm? Well, we need to communicate basically with these devices in every round of the method. We have to ask everyone, please send us a gradient, send it back to the server. This is costly. So we try to measure cost in terms of communication. This is maybe a bit vague, but intuitively we can think of it as, whenever I ask someone to send me something, this costs 1 unit price. Okay, and now if you ask someone from optimization community and say, please reduce communication round, they will say, this is easy. You're not using the optimal method. Just use a method that uses fewer iterations. For instance, like accelerated gradient descent. And automatically we can improve here the estimate. So we can improve the communication, we cannot improve the stochastic term. This is already optimal, but we can improve the optimization term with acceleration. I'm not advocating we should use this method in practice. I'm just saying if you formulate the problem in this way, then this seems like a good approach. Okay, and then the question we now ask is, can we converge faster than this baseline? And no surprise, but we talked a lot about this week is we can, a simple idea to reduce communication is we allow the devices to do more work before they communicate to the server. So one variant or one idea is algorithm called local SGD. Here I use a parameter k to denote how many local updates every device should do before communicating with the server. So we have seen this idea for this dloco method. We had several talks. We have also seen it for this federated reinforcement learning talk. I think it's always the same, maybe slightly different notation for all these quantities. So what happens is, we synchronize the models at some time step, visualized here by these tiny symbols you cannot see. So after averaging, everyone has exactly the same model. When we do more and more local steps, we keep forgetting information on the local devices. We start overfitting on the local data. Yes?
Can you clarify the communication bound a bit? So if you go back to the communication bound,
Yeah.
I'm trying to understand what.
This, yeah.
So what is this? Is it a number of communications constraint? Is it a constraint of the number of communications in order to achieve the same optimization rates?
It's more like a upper bound. So I measure here communication in rounds and activate all the devices in every round. They do some computation, send it back to the server. And this is just like a upper bound. If I run this algorithm, I know I can prove in the worst case it takes this many iterations or rounds to converge. So in this sense, it's more an upper bound on the communication. But
an upper bound on the communication in order to achieve what?
In order to achieve a solution with accuracy epsilon. Yeah, so epsilon is here a parameter that you can set freely, and then we give results for every epsilon. We give an upper bound that holds.
What is the constraints on every node? Because if every node has the whole data, then you communicate to 0 time. I'm not understanding.
Yes, yeah. So this is what we will go to in a very second. I mean, so far we assumed like, okay, every node has access to some part of the data. So, and we don't assume any. I mean, so far we don't assume anything. This could be the same data or data from the same distribution. It could also be data from a different distribution on every node. Our objective is just to average to minimize the average loss. So we want to be good for the average of all data. And this method, because we communicate in every round, doesn't require no assumption on the how the data is distributed. So we can solve this problem. I mean, yeah. I mean, we cannot allow the devices to be too clever. They're just allowed to do one gradient step computation, and then we have to average on the server. But this is then the result we get for this method. Okay, but this, okay, so why did we start looking into these methods? And okay, one explanation is, no, people were using it in industry. We have seen this Gboard application talk yesterday. Also something we figured out quite early, even if you're not working in a distributed setup, even if you work in a data center, when you can somehow distribute the data as you want, this method seems to have some advantages in the sense that you can use larger batch sizes or larger effective batch sizes to converge to similar accuracy. So if you increase the batch size for mini-batch SGD, at some point it starts to saturate and the accuracy drops. If you instead do more local steps to keep a bit more variance between the models, this seems to work much better now. So this is I think also now rediscovered in all these dLoco papers, and I think, yeah, we really need to prove why this happens. I don't know the answer. And okay, other motivation, we have seen a lot already this week. I want to mention another method from authors at this workshop, but not in the audience. No, there's a bit similar, but a bit orthogonal idea. Somehow it's more an optimization view. We could say, okay, instead of just thinking of these devices, they compute gradients, they use a specific method. We could also say, the devices can use any method they want, but we somehow regularize the problem by saying they should not move away too far from the last synchronization point. And to some extent, these views are a bit equivalent if you set the parameter like inversely proportional to the step size of local SGD. We would expect to behave that these methods behave very similarly. So, okay, but now, okay, going back to the question now, what can we now prove for this method? This kept us busy for a while, and. Okay, to summarize, so one type of result we can prove, and for simplicity, assume that the noise is like 0. We, show that the number of iterations, the number of communication rounds we need, depends somehow on, the smoothness over epsilon. So this is this optimization term. We don't expect that we can remove it. Plus, there is another term that depends on some weird zeta parameter. And this is exactly measuring somehow the heterogeneity between the devices. So if every device has exactly the same data, then no matter how many local steps we do, it should not really matter. We can converge. If the devices have different data, then we have a problem, and we somehow need to control this heterogeneity. And one of the parameters I think we converge to is, at least for convex tasks, it suffices to measure the difference in the gradients at the optimal solution. And because we write the optimal solution with x star, this quantity, we call it zeta star. It's somehow quite a weak assumption. We don't assume anything anywhere else in the space, just at one point.
So what is n? N is the number of devices?
N is the number of devices. Yeah.
But it has nothing to do with the samples per device?
No. Yeah. N is just the number of devices, and the number of samples per device would go into this sigma, but somehow
In your model, the samples are just random?
The samples are random, yes.
And this is so gradient f sub I is not stochastic. That's so all the data are on.
Yes, okay, I'm not saying the methods would not work otherwise. I just simplified the result. There would be another term depending on sigma, and this, okay, there will be a nice term, sigma square over n, this linear speedup, but then there will be another term mixing a bit sigma with zeta, and it just does not look super nice. But we have also the perfect understanding for the stochastic case. Okay. And I added this small remark, because this is a workshop on heterogeneity assumptions. A bit a stronger assumption people often use is one can also define this gradient difference like globally. But this is a very, very strong assumption. Somehow it really enforces all the functions need to be very, very close to the average everywhere. Yeah. Okay, and then we worked for a while. We were really focused on this problem. Why is this similarity term appearing? Can we remove it? And also Peter gave this tutorial explaining other methods like proxskip, scaffold, where we really worked to basically with the goal to remove this dependence on the similarity by designing better methods. So we want to correct for this bias while still doing local steps. And this is the results show, okay, we can converge a number of rounds that should not depend on the similarity. So this is an upper bound. This does not say these methods in practice will not depend on the heterogeneity. It's just like in the worst case upper bound is somehow does not depend on this parameter. Okay, and if you don't know how these methods work like, I will have an example in a few slides. But for now, I want to put the focus on this parameter L. Now, somehow, this L appeared. They say it's an optimization term. There's nothing we can do about this parameter L. But it's very, I don't know. I think these results are not really still not reflecting so well how the methods perform in practice. And then I think with the,
the distribution of the stochastic noise is the same in all of is the same everywhere?
No. So it can be different on every device. So this is what we try to capture with this zeta parameter. We just say every device can have different data, different distributions, and we somehow try to condense this to one single parameter, which is maybe questionable if this is the right parameter. But after this, we allow every device to have different distributions. Yes, yeah. And okay, for these formulas, I also assume zero noise to simplify the formulas. But we also have expressions for the general case where the noise is different on every device, let's say. Okay. And already, I mean, in this scaffold paper, we already had some special results for quadratic functions. We can be better than this upper bound. So this is a bit, what can we do? So there was a big interest in the problem. Can we prove rates that do not depend on this smoothness constant now? Because this seems to be now the barrier that we need to overcome. And this comes a bit now to the topic of the talk. And very luckily, I spent so much time on the introduction, I will not cover everything. And but it's based on two papers with Xiaowen and Anton. Xiaowen is on the job market soon, so if you have some jobs anywhere, please let us know. And yeah, this is a bit older paper that I will probably be able to cover. And there's some newer results I will maybe just briefly mention. Okay, let's focus again on the question. We had these local methods, they work quite well in practice. People also at this workshop, they write papers saying, well, the unexpected effectiveness of this method, can we explain why this works so well? And one way to explain why it maybe works better than these upper bounds we had so far is to try to see, can we measure the similarity among these clients in a different way? So not with this gradient at the optimum, but maybe differently to get a better understanding of how these methods work. And one quantity, I mean, not necessarily introduced by us, the other papers I mentioned below, but I think it somehow is very beautifully captures the right measure for this type of methods. So what we need to look at, we need to look at how different is each function from the average. And how does this difference change in the space, basically? Because somehow if one function or one client is always very different, I think it's a very easy problem. We can just treat this as an outlier, and it's always an outlier. If one function is always very close to the average, I mean, that's a good situation, and we can trust this is always a good representative of the population. And the only difficulty comes if somehow the one client constantly switches between the average and far away, and then we need to be careful. So one way to put this in formula is to say, write it like this. So we define the function hi as to be this difference, and then it's essentially a definition of smoothness of this hi function. And we introduce a parameter delta that now measures similarity. Okay, to give an example, let's look at quadratic functions. So we can assume every function fi is given by a quadratic with a Hessian hi, a linear term bi times x, and some constant ci. When we plug in this definition, we see that essentially only the difference of the Hessians ai to the global Hessian appears. And if we can have an upper bound on this difference, then we have an upper bound on delta. Okay, that's one thing. I mean, before we assumed always smoothness, and we can show that any smooth function will also satisfy this expression, but the parameter delta can potentially be much smaller. And now we would like to basically come up with results that whenever there is a L in the convergence result, we replace the L with a delta, and that, yeah, I don't know, would to some extent explain why the methods can be faster when there is a high similarity. Okay, and to maybe the somehow easiest, or I think quite elegant way to present this is by a method maybe not so often used in practice and slightly different to this local SGD, but it's based on this proximal, this FET-prox method we've seen before. The problem with this FET-prox method is now that somehow it's not really accounting for the different possibility that the devices can have different distributions. So we cannot prove this result for FET-prox, but we can make a modification to this method by somehow correcting for this bias that we have on every device. Okay, this is not really a surprise. People who worked on maybe scaffold, all other methods, this term is very, very commonly used. So we look at how different are the gradients on the, how different is every local gradient from the global gradient. And this drift or this bias term we can use to correct in the method. Yeah, that's a question.
If you don't add the correction term, then do we know that Fedprox has like a L over epsilon like low bound, or we just don't have an analysis?
Yeah, okay. I put it on the slide before with this zeta star. So I think, okay, yeah, I don't know. There is definitely no proof in the original paper. We tried a bit, but I think it's not written carefully. But it's.
But is it like, is there a lower bound that matches your upper bound?
Yeah. Yeah, so I'm not saying it's not possible, but it's would be very unlikely. So if with this correction, somehow it works. And this is actually an old method. No, actually it's predating all this era. Somehow it's from basically 2014. And also Natis Rebro was on the paper. So they call the method Dane. And yeah, they developed this for minimizing distributed quadratic functions. And okay, what we somehow did first is somehow extend their old result to general class of convex smooth functions, and not just quadratics. No, but somehow the method is not really new. It's okay, it's the proof, and we can show that okay, we need to know this parameter delta. We need to set the regularization carefully, depending on delta. And then we can prove this method requires only the number of rounds required by this method only depends on delta and not on L. So in highly similar, I mean, when all functions are almost similar, we can converge in 3, 4, 5 iterations or rounds of communication. Okay, we can now dive a bit deeper into this. Let's do this quickly. I think it's more going now into details. So we had first this whatever best method we can think of, maybe fast gradient or accelerated gradient descent, but the rate depends on L. And I mean, we can prove it can never be better than this. But then we have this different method. Some people call it Dane. We try to come up with a more neutral name. It's like just a composite gradient method, nothing extra. You can even find it in maybe textbooks under this name. And this method just depends on delta. Now, depending on the ratio of L and delta, this can be faster.
So when we say CGM can be faster than FGM, we just mean the upper bounds are smaller. Exactly,
yes. Yeah. Yeah, and exactly. Now you see already a small. I mean, these bounds are not comparable if the delta can be as big as L, yeah, but yeah, we can fix it. Yes.
How much do we understand?
So the fast gradient method, that's not just an upper bound; it's tight. So for CGM, it's an upper bound which is lower than a tight upper bound for fast gradient method. So it's actually proven.
Okay.
Yeah. Okay, so I have I mean, this is I will do this in 5 minutes. Let's forget, yeah.
Tight in what sense? Tight in the sense of over all possible algorithms?
Over all possible, it's algorithm dependent lower bound, which shows that for that particular algorithm, for any instantiation, it's tight. Okay. But it's also tight over all first order algorithms that do not assume determinism.
Okay, thanks. Yeah, okay, somehow, okay. I mean, okay, so one small detail I was basically hiding, I was in the definition of this method somehow requires to solve this proximal subproblem every step, and somehow I assumed, oh, this is always easy. But if you look at the details, we require some condition to say that, okay, we need to solve these subproblems to some accuracy. Maybe we can measure it in the norm of the gradient of the subproblems, so should be small. But this accuracy condition depends on the number of rounds we have done so far. So when we run the method for longer, we need to solve the subproblems more accurately. Yeah, this is maybe an issue, maybe not, but at least when you account carefully, there is another logarithmic term in the number of rounds that will appear. And okay, we looked a bit into this problem. How can we solve it? And we found a, I think, quite elegant solution. And the way how it works is, instead of regularizing the method at the old synchronization point, we compute a more optimistic point in the future. So some people call this like a look-ahead step or an extra gradient step. So we try to predict where the method would like to move. And then one can use this new point as as reference point where you want to keep close. And for the special case, when we just have one device, this method can be seen as a special case of this Montero-Swaiter algorithm that was designed for accelerated. It's basically an accelerated method, but you can set the parameters in a way that it's not accelerated, and then it matches exactly this thing. Yeah, so this is very nice, and what we can then prove is that to solve every subproblem, the accuracy condition for every subproblem does not depend anymore on the number of rounds. It just stays constant, so we can remove this log factor. That's the main benefit. So to summarize, we have seen several methods. Okay, so in the last part, I explained, we can remove this log factor. And but I will not explain that this whole framework also allows to design somehow accelerated methods for the outer loop. Basically, on the server side, you can run accelerated gradient descent. And then you can reduce this dependency on delta to square root of delta. Yeah.
So with acceleration, you just lose the advantage over fast gradient?
No,
Because if I multiply both...
No, exactly. I think what should be observed now, we are not beating optimization bounds. The number of computation stays the same. We're just shifting computation from the server to the devices. And I think this result, it works for any parameter, so you can have any ratio you want. Somehow the computation stays the same, but you can basically decide how much you do on the server. You can do as little as this one. Yeah, and very related work, with very different method, similar result, is in this paper by Kovalev and al. From 22. So I think it's good to compare. Okay, just one slide on experiments. So please ignore the red curve. This is like with acceleration, so it's a bit a separate field. The blue and black curve are just these two methods, one with destabilization and one without. And here on the right, we show the total number of gradients we need to compute. So even if it's just a log term in the rate, I think in practice it can still make a big difference in number of computations we really need. Okay, so this works quite well, I would say. There's also this variant in the paper. You will ask the question, what can you do when you don't know this parameter delta? It's like a hyperparameter. You need to know this hyperparameter to run the method correctly. One can also try to measure this by just the gradients that you collect. We can try to measure what is the correct parameter delta, and then we can plug in this estimation as our parameter. And this gives this blue curve. So in some cases, it can really accelerate over all the other methods where we just use a constant upper bound for this delta parameter. Okay, but I feel, okay, I'm overfitting too much to the convex setting. And okay, this is, I want to go back at this at the very end. I have 5 more minutes to discuss a slightly different topic. And just to make this method more practical. And again, as before, this is not we are not the only ones working on this. No, there are many people who already thought about this problem. What is the problem? So to implement this correction, like in maybe scaffold or in this method, one limitation is we need to have an estimate. I mean, we need to have the full gradient every round. This means we need to talk to all clients every round to implement this method as it's written here. But in practice, we would like to just ask a subset of the clients to send us some information. And now the big question is, how can we adapt the method in such a way that it also works with client sampling? Okay, and I think, I mean, the strategy, what we want to do is quite clear. We want to replace this gradient with some estimate. But now the question is just, what is a good estimate? And I looked up, there was some paper called Federated from, by Jian Li, who also presented yesterday. And I think they proposed to just use some unbiased, I mean, a mini batch estimator for this for this gradient and to plug it into the stain method. Okay, there's unfortunately no proof, and I also think it's quite difficult to prove with this type of estimator. So maybe the next best thing is let's try to use some variance reduction. So we know we have variance reduced estimators. Let's use them. And indeed, one can do. And okay, maybe a bit of history. So there is people like Ahmed has a paper on this for the convex setting. So I think there's nothing to do anymore for the convex case. So we focus now, shift our attention to the non-convex setting, where the correct result is not known. And there our accuracy condition is, okay, we want just to reduce the gradient norm to some small parameter, I mean smaller than epsilon. And we can prove something like this. Now we just run Dane. Whenever there is a full gradient, we replace it with a SVRG estimator. And then we can measure proof how many rounds do we need for this method to converge. And let's go over this result. So there is one term which is a bit artificial, but it's n. We sample S clients every round. To initialize the method like SVRG, we need one full gradient at the beginning. So this is the cost to get one full gradient. In every round, we can only talk to S clients, so we need n over S rounds. Then again, there is some optimization term. We should maybe ignore it. For the moment, it somehow depends on another delta parameter that but think of it as being equal to delta. And then there is another part that somehow depends on n and the ratio of n over S. So the number of how many clients we activate, or what is the ratio of clients we activate. I mean, this is an upper bound. And I just say, okay, it's not optimal because we can improve it further. Okay, what would this bound say? Well, if you sample the number of clients to be approximately n over 2/3, so still a quite big fraction of all the clients, you will get you can prove that your upper bound will be the same as you get from activating all the clients all the time. So you don't need all the clients. But can we reduce this ratio even further? And yeah, there is a good reason to believe it can be done. That's why we spent some time there. And we basically just try to explore what are can we, instead of SVRG, can we use different estimators? So there is another one, maybe Sarah, That's also commonly used for non-convex optimization. And as I said before, no, this is not a new idea. People have tried, for instance, a paper by Mishenko, where they basically come up with a good method for the full participation case. And then they add a small result that also covers partial sampling. But this is really not the main result of the paper, because why do I emphasize this? Because the result is quite pessimistic. They require a huge mini batch every time, and this is maybe not the ideal answer yet. Yeah.
When you say similarity, similarity to what? To the average of all, or are we still assuming that we're just trying to compete with the average of all the FIs?
Yes, yeah. So that was maybe not so clear. So we basically know that in this full participation setting, we can get we have a method where we know the number of rounds depends only on this delta parameter, and this is what I mean by similarity. And now we want for the partial participation setting also a method when I know the delta, I can give an upper bound on the rounds that just depends on this delta parameter, but not on other parameters. So somehow the method needs to know the delta to be correctly implemented. But yeah, there's maybe similarity aware is maybe not the right word to put here, because I just mean the same thing again for similarity. Yeah. Okay, so last slide on this. So I don't fully understand the reason. So we somehow discovered using the Sarah update was not really working. We had to do somehow to combine the Sarah plus some type of momentum term. And this momentum term, okay, is basically the old estimate that we want to stabilize. And we can use any unbiased estimate, for instance, like SVRG estimate, to somehow give us additional information on the quantity that we want to estimate. Yeah, so I would love to give more intuition here. We don't fully understand it. It's very similar. There are these methods. There's some other estimator called Storm, and there is a method called Mars. And they look very similar, but they're all different. So it just maybe depends a bit where this beta is placed. But these are all, on the formula, they're all different formulas. But maybe it's a very similar idea that's going on. And if we can present it, we are working on trying to make nicer slides to present the reasons a bit better. Right now, it's more like this is what comes out of the proof to prove the result. And what is the result? Well, we could remove this square root n over s term at the end. Okay, it's basically saying, okay, we can now implement this method. We just need to activate square root of all the clients. So s about square root of all the clients is enough in every round of communication. And we can converge as fast as we would converge with activating always all the clients. Yeah.
Slightly confused. So you're not making any zeta star assumption here?
No.
But in the partial participation setting, you have a lower bound that depends on zeta star, in the same sense that you have like a lower bound that depends on sigma star for like stochastic optimization. Because you have to pay the... Yeah, but we also use variance reduction to tackle this zeta somehow. But even with variance reduction, you have to pay, like if you're doing stochastic optimization, then you have to pay in sigma star. The same way if you're doing partial participation, you have to pay in sigma star. But I think it's maybe hidden here. So this n over s is the cost of the initialization, and this takes care that we start with a good point, where basically we average once all the devices, and then the zeta star disappears. Yeah. But let's discuss offline. Okay, so to summarize.
This is finite numbers.
Yeah.
No, but yeah, I know, but the zeta star assumption in the finite sum setting with partial participation is equivalent to the sigma star assumption for SCO. That's why there's a zeta star lower bound in the partial participation setting. But I agree, the n over s can kind of hide it because you're,
Yeah, I mean, okay, so what I want to have somehow 3 questions. Yeah, so what should we optimize for? Now, so somehow the screen say, I mean, when you look at some operation system have this screen that changes every time. And this morning it showed me some windmills. And I think it's a good thing that we are chasing windmills when we do optimization. Now we are given a problem, we just run for it, we optimize. And maybe we optimize too much. Now I think this is a bit the balance that we should try to come. In this, what I showed here, now we try to optimize for we set communication round is our target. We minimize optimization rounds. And I would say, yes, this is a quite useful quantity. One should be perhaps a bit more careful with this sampling type of thing, because we discovered that there's a lot of things hidden in the details of the assumptions in this paper. Maybe activating S clients, do we really assume we can have a uniform sample of S clients? Or can we choose the clients we want to activate? This all makes a difference. And one should treat this more carefully. So we have a lot of discussion on this in the paper. Another question that came up now, what is the right notion of heterogeneity? We started with the zeta parameter. I tried to convince you delta is a better parameter, but actually it's maybe overfitted to this type of algorithm. We tried also to prove, let's say, like local SGD with this assumption, but there we already need more assumption to tackle the similarity somehow. Yeah, and I took this quote from the description of the workshop. No, I mean there is still a need to come up with better definitions that actually, I don't know, reflect a bit what people care about in practice. No, and if we can measure this more precisely, we can also develop better methods for this. And yeah, exactly. So federated optimization now is very different from federated learning. I can write here, oh, let's solve this prox problem. It does not cost me anything. In practice, people maybe don't want to solve this prox problem. And I'm very happy now to discuss any insights. What do you think makes sense in practice? What does not make sense? What is maybe some hidden assumption we could try to add to our theory to make it more relevant? Okay, so with this, close. Thank you. The original title of the talk was Federated Optimization, and I changed it to Federated Learning just to be a bit more general, but I completely myself also see this is more optimization view on this problem. But it's well defined, we can solve it, but we might be overfitting on a bit the wrong problem to solve. Yeah.
Yeah, questions?
Thank you for a great talk. Interesting research as well. So I'm wondering, maybe you talked about it. How do you choose the parameter lambda, the strength of the proximal?
Yes, so it's from the theory perspective, it should be delta. So if you know how similar, or if you know upper bound on the similarity, you should choose this as the lambda parameter. And then I had this, it's not a heuristic, no, it's more an adaptive version. You can also try to measure this delta on the data of your problem and then use this estimate while running the method. But yeah, this is an additional hyperparameter.
So the reason that I asked is because I was thinking about some non-convex setting where you probably want to choose lambda to be very big so that it convexifies, and then it seems that like at each step you make very little progress, but overall you can probably even prove some polynomial rate of convergence as well at the cost of choosing a larger lambda.
Yes, yes. Okay, thanks. Yeah. Yeah, okay.
There are other questions that I can.
Yeah, you can go.
I'm still not convinced that for the FedProx algorithm, you would need something
which is even like a geometry dependent assumption, like going back to maybe Peter's talk, but also like this Bolerical papers, we know that you can get like geometry independent rates there, and it appears that you get the delta dependence only because you add the gradient based correction term. Because you can cast the Fedprox algorithm as a Bolerical algorithm, right? So with the correct lambda, you can cast it as you can cast the Fedprox algorithm for the correct lambda as like a proximal algorithm, I believe. And then I suppose you don't need delta.
Definitely because there's gradient correction.
Yeah, so it seems to me that we should be able to prove something stronger for Fedprox under maybe
Okay.
you need like an interpolation regime, but
Yeah.
yeah.
I don't know.
I think Sebastian is right. That Fedprox is not the kind of right algorithm in some sense. That this correction is missing. It's
Yeah. Yeah. I think that there may be a different. Yeah.
Okay, let's maybe talk.
Okay.
Okay, thanks Sebastian for your great talk. Okay, now. As a next speaker we have Gauri Joshi. She